本场讲座是台湾桥梁计划的最终场。自5月4日起，我们特别举办了对话诺贝尔特展。活动开始前，让我们先观赏对话诺贝尔特展介绍影片，借此对本系列活动予以回顾及展望。Today's lecture brings the Taiwan Bridges program to a close. Since May 4th, we have also presented the In Dialogue with the Nobel Spirit special exhibition. Before we begin today's event, let us first watch an introductory video of the special exhibition as a brief look back and ahead.
Next, we will take a moment to introduce this series of events and the curatorial concept behind the exhibition. The exhibition In Dialogue with the Nobel Spirit synthesizes the achievements of the Nobel Laureates lecture series over the past 2.5 years, bridging world-class intellectual achievements with the vibrant spirits of National Taiwan University. We deeply thank the Swedish Representative Office in Taiwan for providing the authorized Nobel Foundation panels. The celebration of Nobel Day has inspired us to further cultivate the spirits of the Nobel Prize in Taiwan. This vision has been expanded through the Taiwan Bridges program, a nationwide initiative with a profound mission to share the transformative insights of Nobel laureates across the entire country. In this series, NTU has organized 11 key lectures. We aim to harness the wisdom of these academic giants to propel Taiwan toward greater academic excellence. We began this journey in 2023 with 5 lectures. This initiative has been made possible by Mr. Raymond Song's generous support for talent cultivation. Building on that, the 2025-26 NTU Nobel Laureates lecture series followed with 6 highly anticipated lectures. We are now actively preparing for the final session of this series on May 6. To commemorate this journey, this exhibition brings to life the rich insights from these lectures. You will gain insights into the original spirit of the Nobel Foundation, explore the intellectual ideas of the laureates, and engage in an interactive experience that transcends time and space. We have set up dedicated areas for multimedia presentations, signed posters of the speakers, and a message board. We warmly invite you to share your thoughts and leave a message to express your appreciation for Mr. Alfred Nobel and laureates. Finally, National Taiwan University hopes that this exhibition will respond to and carry forward Alfred Nobel's vision of working for the greatest benefits to humankind. Please join me in a round of applause to honor his legacy. To symbolize, thank you all for showing your heartfelt appreciation of Mr. Alfred Nobel.
接下来，让我们观赏今天的主讲者2017年诺贝尔化学奖得主 Joachim Frank 教授的介绍影片。Next, please enjoy an introductory video about today's speaker, 2017 Nobel Laureate in Chemistry, Professor Joachim Frank.
The Royal Swedish Academy of Sciences has decided to award the 2017 Nobel Prize in Chemistry jointly to Jacques Dubochet, Joachim Frank, and Richard Henderson. And the Academy citation runs, for developing cryo-electron microscopy for the high-resolution structure determination of biomolecules in solution. Für die Entwicklung der Kryoelektronenmikroskopie für die hochauflösende Strukturbestimmung von Biomolekülen in Lösung. Pour développement de la cryomicroscopie électronique pour la détermination haute résolution de la structure des biomolécules en solution. за развитие криоэлектронной микроскопии высокого разрешения для определения структуры биомолекул в растворе. And you see pictures of our new Nobel laureates on the screen above me. Jacques du Bourget was born in 1942 in Switzerland. He studied in Basel and in Geneva, and he is currently honorary professor at the Université de Lausanne in Switzerland. He's a Swiss citizen. Joachim Frank was born in 1940 in Germany. He got his PhD at the Technical University in Munich, München, and he is currently professor at Columbia University in New York. He is nowadays a US citizen. And last but not least, Richard Henderson was born in 1945 in Scotland. He received his PhD at the University of Cambridge in the United Kingdom, and he is since many years at the Laboratory of Molecular Biology in Cambridge. And I think he is the 15th Nobel laureate from that laboratory. Rather impressive.
Jacques du Bourget, Joachim Frank, and Richard Henderson. Your work has led to the development of cryo-electron microscopy for the high-resolution structure determination of biomolecules in solution. That is a truly great achievement, a truly great achievement. On behalf of the Royal Swedish Academy of Sciences, I wish to convey to you our warmest congratulations. May I now ask you to step forward and receive your Nobel Prizes from the hands of His Majesty the King.
And now Joachim Frank, born in Germany, and at the time of the announcement, he was associated with the Columbia University in the United States.
I was sort of half asleep and half awake because we were worried about our dog. Our dog had been waking us up around that time. And so I was worried it was going to be the dog again, but this time it was the Nobel Committee. Yeah. Oh, it was pretty overwhelming, and I couldn't really find the right kind of words. You know, I had the urge to be very sophisticated in my answer, and all I could say was, you know, this is wonderful. This is wonderful. Well, it changed quite a bit because there have been so many media requests for interviews, there were requests for information, for pictures. There were so many congratulations from everywhere, from every corner of the world, and from families and friends, also from many people that I'd never heard from for a long time, and then from strangers, from absolute strangers that just happened to live in the same area in Germany. These kinds of things. So it's really it's been sort of a non-stop. You know, I can think of my life entering a new phase of maybe completely new projects, and also a phase in which I can afford to relax and write books and things like this. So I can I see the rest of my life open for a lot of explorations that I can do much easier than I could do before. It's an acknowledgement that I sort of join different kind of ranks. And there's a comfortable feeling about it, but also an uncomfortable feeling about it. You know, it's a feeling of guilt that, you know, I should not be in this position. You know, there's something. You know, something must have gone wrong here with judgments, you know, because there are so many people that I know are deserving of this honor. And I know about the difficulties of making these kinds of judgments, especially because there are only 3 people that can be selected. But in this particular category this year, I think people were very happy in the community with this kind of choice of the 3 people. And I think I got the same feedback from the other 2. I know very well. I've been I met them very many times in conferences. Sometimes we invited each other to give presentations. We never collaborated. I think my first encounter with Richard Henderson goes back into the late 70s. There were particular conferences which brought together protein crystallographers with electron microscopists. They were co-organized by Max Perutz and Walter Hoppe. Walter Hoppe was my mentor. Max Perutz, you know very well. Yeah, in my field, I looked up to Aaron Klug, and he, together with David Duracier, who is here, did the first 3D reconstruction from electron microscopy. And Aaron Klug was a single one who got a Nobel Prize in chemistry, but it was jointly for 3-dimensional reconstruction as well as the structure of the nucleosome. So it was sort of divided between the 2. Then, of course, the inventor of the microscope, the electron microscope, Ernst Ruska, he got the Nobel Prize almost as an afterthought. It was really embarrassing because the decision was made to give the prize to the atomic force microscopy, and then he was simply added on as a third person, even though his invention, went back 1931. And atomic force microscopy, in my opinion, was overrated and has receded to a niche meanwhile. But the transmission electron microscopy really flourishes, as you see. And then, of course, the prize that I was touched by was the one for the ribosome structure, because I've been working on the ribosome quite a bit, and also the cryo-electron microscopy in my lab has made a contribution to the X-ray structure itself, to the phasing of the X-ray structure, as acknowledged by Tom Stites. So the prize in 2009 to Ada Yonath, Venki Ramakrishnan, and Thomas Stites was something that sort of emotionally touched me, because somehow, I thought, well, I did some contribution to the ribosome, and maybe I could have been part of the club if the club had been 4.
You can take me high.
各位长官、各位贵宾，欢迎莅临国立台湾大学宋公元先生顶尖研究讲座诺贝尔奖得主演讲系列。Ladies and gentlemen, welcome to the NTU Raymond Song Chair Professorship of Distinguished Research Lecture Series. 演讲开始前有几项宣达事项，请各位贵宾协助配合。Before we begin, here are some housekeeping announcements. 本会场请勿进食或饮用茶、咖啡等有色饮料。饮用水请置于密封容器中。Except for water in closed containers, food or drinks like tea and coffee are not allowed in this lecture hall. 如需登记公务人员终身学习时数及台大学生学习历程，敬请扫描出入口的 QR code. If you are civil servants who want to register for government employee lifelong learning, or students who want to link this learning record to your e-portfolio system, please find and scan the QR code at the entrance. 请掌声欢迎 Joachim Frank 教授. Please put your hands together to welcome Professor Joachim Frank. Ladies and gentlemen, welcome to the 6th lecture of the NTU Raymond Song Chair Professorship of Distinguished Research Lecture Series. First, we'd like to express our sincere gratitude towards the Taiwan Bridges program and extend our welcome to the members of Taiwan Higher Education Nobel Laureate Association. It is our honor to have 2017 Nobel Laureate in Chemistry, Professor Joachim Frank, as our speaker today. But first, please join me in welcoming our host, Professor Chen Wen-Chang, President of National Taiwan University, to deliver his opening remarks.
Nobel Laureate Professor Frank, and also our co-organizer, the chairman of International Peace Foundation, Dr. Oben Morowitz, President Ho, and our faculty and student, distinguished guests. Good afternoon. Yeah, it's my great honor and pleasure to welcome Professor Frank from Columbia University to deliver the lecture for Raymond Song Chair Professorship. And it is also the final lecture of Nobel Laureate lecture series, which we call it the Taiwan Bridge Program. It is organized by National Taiwan University and also academic Sinica with the International Peace Foundation, and also 12 higher education institutes join these bridge programs. And the purpose of this bridge program is to have a dialogue with, between Nobel laureates, with the Taiwan society as well as higher education. And this is the final one of the Taiwan Bridge program. And it is also the beginning of the new chapter of Nobel laureates to Taiwan, I believe. Let me give a very brief introduction on Professor Frank. He received his degree from Germany and then teach at the Columbia University. And his expertise is to develop a low temperature electron microscopy, in particular to construct three-dimensional structures of biomolecules in solution, in particular for the case of protein and others. Before that, it is very difficult to use the electron microscopy to probe the three-dimensional structure of biomolecules because electron beam, they will destroy the biomolecules. And Professor Frank, he developed a cryo-electron microscopy, and they can construct the three-dimensional biomolecular structures in solutions. Therefore, we can see the real structure of the biomolecules or others biomolecules. I think it's very important for this kind of technique, in particular for the application of medicine or drugs. And that's why he won the Nobel Prize in Chemistry in 2017, because it's a very big impact for that. Even myself, I'm not a biochemist, but I am a polymer chemist. And sometimes we need to use the cryo-TEM to probe the soft material structures. So I believe that the technique he developed is also very useful for probe all kind of soft materials in particular in the three-dimensional structures. So it's very nice we have opportunity to listen to his structures. Professor Frank not only received the Nobel Prize in Chemistry in 2017, he's also the member of National Academy of Science in the United States and American Association of Arts and Science. So it's really an honor and also a pleasure to have him in NTU to deliver his lectures. So please join me to welcome Professor Frank for his lectures.
Thank you very much. Is this working? Okay. It's an extraordinary honor to be here. I would like to thank the President and the International Peace Foundation to bring me here. It's not the first time that I've been in Taipei. I discovered from my long CV, by editing it, found out that I was here in 1999 as a guest of the Academia Sinica. So this morning I had a discussion with students, and I was amazed about the knowledge that was already expressed in the question. So I think for those students I don't have any message. However, I thought the lecture would be an opportunity to talk about the way the entire field developed, what exactly my contributions were at a particular time, and then go on to go into my vita itself, the way I essentially went from one station to the other and developed the ideas, and then followed by giving an impression about the current applications of the technology. So essentially I'm trying to cover 3 or 4 different aspects of this entire field. So this was what I found in my CV. So today's medicine is guided by the knowledge of the way biomolecules are built and the way they act in concert in the cell. And with that knowledge, effective drugs can be developed, small molecules that are designed to bind to the target molecule and thereby change its behavior. And this, in a nutshell, we understand under the name molecular medicine. At the time when I started, there was no such thing as molecular medicine. The knowledge of structure, dynamics, and organization is required on different scales. And these are all associated with the fields of structural biology and cell biology. So you have to imagine that molecules are tightly associated in the cell. They interact within the cell, and this is just this little imagined snapshot of the way molecules interact. If we want to find out how they interact, it is very difficult to make this out in this kind of crowded environment. And this is the rationale for in vitro studies. We want to take the molecules out of the cell and then individually study how they interact in pairs and threesomes and so forth. So we also have to understand that molecules don't just interact in a cell at random by collisions, but rather they are organized in molecular machines. So a given process actually involves several molecules, and there's a certain time direction involved. So we talk about processivity. So we wish to know the structure of all components, but also the way they interact dynamically. And the result is then a targeted drug development to combat diseases. And that's in the keyword of molecular medicine. And so I repeat, we studied a subsystem in isolation in vitro, hoping to approximate the processes in the environment of the cell. And this can be phrased under the word of reductionism. So structural biology. It has been mainly focused on the structure of biomolecules in isolation, and this knowledge is of crucial importance in molecular medicine. We need near atomic resolution, 2 to 4 angstrom, to determine the position of every single atom in a protein. And the structure determination is mainly done nowadays by X-ray crystallography or electron microscopy. And I see, for those who are not so familiar with biochemistry, I just want to show the kinds of depictions of molecules. Here's a molecule of hemoglobin, and the cryo-EM map looks like this. And if we find the position of every single atom, it looks like this. So the atoms are not connected, and we see simply a cloud. And we see this without any differentiation, and we don't know how they are connected with each other. And then there's another depiction, which is a ribbon diagram, in which we simply follow the directions of the protein chain, which may be folded in an alpha helical way, or in beta sheets, and so forth. So we simply show only the elements of secondary organization. So this is all the same molecule. These are just different depiction of that molecule. And I'm showing hemoglobin for a reason, because it's one of the first molecules, protein molecules, that was studied by X-ray crystallography. So X-ray crystallography goes a long way back, and it was essentially started by Max Perutz and John Kendrew. The molecules can be made to form crystals, or they come organized in crystals, and they arrange closely packed in regular order, and the order is very precisely regular. And in that case, the atomic structure can be determined by X-ray crystallography. So an X-ray beam shines on the molecule, and then we get diffracted rays. And the position of these diffracted rays on a fluorescent screen or a camera has the information on the structure. And there's some bit of information missing with the phases, but there are ingenious techniques that have been developed in order to recover the phases. So then the entire structure can be determined. And here's Max Perutz with his student John Kendrew at the Nobel Prize in 1962 in chemistry, and they're shown with a model of hemoglobin. At the time, that model was built, had to be built with wireframes or styrofoam, and there were no other ways of depicting it. But that leaves a big gap in knowledge. Many molecules will not pack in regular order into crystals. How about imaging molecules directly? So to look at molecules, can we use light microscope? No, they are way too small, even much smaller than the wavelength of visible light. And so we need a microscope that works with a beam with a much smaller wavelength. But the setup of microscopes that work with light or electrons are very similar. So you can see an analog arrangement here. Light microscope, you will recognize the way the beams go. You have an object. Here's a lens, and the lens forms a magnified image. And we use glass lenses, but the resolution is only 200 nanometers, which is half the shortest wavelength of light. Electron microscope here is set up in this very similar way. Here's the lens, which in this case is a magnetic lens, but the path of the rays is very similar. An image is formed, and that is then further magnified. So it was Ernst Ruska who realized that one can actually build an electron microscope using electrons, and this is and the fantastic thing that I realized only recently is that it's only 7 years after the discovery that electrons have both particle and wave characteristics by de Broglie. So here's a sketch of the first electron microscope, and he built it and made it to work in just a single year. And I always take a second here to emphasize when you make a really great discovery that you only know about, make very explicit notes in a notebook that one day this is the only proof that you have about your brilliant idea. So here is a schematic diagram of a transmission electron microscope. Transmission means that the electrons penetrate the object and then they are visualized. Okay, so the object has to be very thin. Let's see. So in the middle there is a column which is on high vacuum. It has to be on high vacuum because otherwise the electrons get stuck within a few millimeters. Electrons are produced up here in the so-called electron gun, and then they are accelerated to a very high velocity in this very small space. And then they fly down here. They're collimated into a thin beam, and then they arrive here on the sample. The sample is half embedded in the objective lens. The objective lens is the most potent lens in the electron microscope. It forms an intermediate image right here, and this image is then further magnified by the projector lenses. And this is still a schematic diagram of a very old kind of microscope where one actually sits here and looks into through a glass on a fluorescent screen. Nowadays, and then one can also has the option of taking pictures with a plate camera. And nowadays, the operator sits somewhere on a workstation and watches as the image is being captured by a camera, by an electronic camera. So we have to realize transmission microscope. What does it mean? We see the object, we see through the object, and this is the idea of a projection. In real life, we have hardly any objects that we can simply see through. This is a jellyfish would be the best example. we see through a jellyfish, and depending on how much the light beam has to penetrate, we get sort of the appearance of a high density or a low density. So we have a molecule which is a three-dimensional structure, and now we see a variety of two-dimensional projections of it, depending on the viewing direction. And from the 2 dimensions, we can get to 3 dimensions by using a theorem that was already formulated by Johannes Radon in 1917. He is an Austrian mathematician. At the time, of course, there was no computer application because there were no computers for this. So the theorem is formulated in Fourier space, and it simply says that if we get a variety of projections, then we can recover the object by transforming the projections into Fourier space, and they become central sections of the three-dimensional Fourier transform. So one can fill the three-dimensional Fourier transform by collecting many projections, and then by some kind of interpolation, fill the entire Fourier transform, and then transform back into real space. So that's how we can get a three-dimensional reconstruction. And the first people who applied this with a computer are Aaron Klug and David Roussier. And they did this in a special case of a helical structure of the bacteria, of a bacteria phage tail. And since it had a particular symmetry, the helical symmetry, a single projection is actually enough to get us all the information. So we don't even have to change the viewing direction. However, this was a stunning achievement in 1968, and everything else, all the development of the fields really built on this. So you already see where I'm getting at. Why do we need crystals at all? Why not look at the molecules themselves as they are? Why do they have to be in crystals? And my mentor, Walter Hoppe, in Munich, had this same idea, and he wanted to solve it by essentially taking the molecules that are sitting on the grid and put them into different viewing directions. So it's essentially a tilt series. The method is called electron tomography. You take a tilt series and then use the theorem that I just told you about, and then we can essentially get a three-dimensional reconstruction of the entire grid with all the molecules sitting on it, and then you can do whatever you want with the individual reconstruction. So the problem with this approach is that you accumulate a vast exposure of the molecule, and so in the process the molecule sort of suffers radiation damage, and in the end you have a 3D reconstruction of a molecule that doesn't look like the initial one anymore. So you destroy what are you looking at. And so I asked the same question, why crystals, but I approached it in a completely different way. I realized that whatever molecules we are looking at always exist in thousands, hundreds of thousands, millions, trillions of copies. So if we had them in solution and get a single image of them where all the molecules are in random orientations, then we have all the information that we need. And we don't even have to tilt the molecules because they have already tilted themselves. And, and since we have so many copies, we can reduce the intensity of the beam to a very small margin. And then we essentially get the information together by integrating over so many different copies. So, in formal terms, single particle techniques means that the structural information comes from images of single, which means unattached molecules that exist in many copies. The molecules are randomly oriented. They are free to assume all naturally occurring conformations. A single snapshot may already give us hundreds of particle views. And as we collect more snapshots, more orientations will be covered until we have enough for reconstructing the molecule in 3 dimensions. So, the method might sound very elegant, but the problems are already coming after you take the pictures, because we don't know anything about the molecules, we don't know the orientations. That's the most important thing. So we don't know the structure, we don't know the orientations of the structure. How do we even get started? So this is where really the problem starts. And so I had to write I had to do a lot of thinking. I had to think about the math of the problem and the computational solution of the problem. I had to develop for myself a workbench of programs. This is a workbench of 400 programs, which we called Spider. And each of these operations is what I call a primitive operation. It's like a primitive Fourier transform, autocorrelation, shift, rotate, all these different things. So you put them together, so each can be addressed by some kind of by command, and you put the commands together. You can string these operations together any way you want, and they communicate with a common database. So each program knows what the other one has been doing, and so forth. So this is how this whole thing started. With this workbench, I could share this workbench with other people. They could program with it, even though they didn't understand the math that is behind it. So this is how the whole thing started. And the most important problems are, how do we align images to start with, which I've found out in my thesis by using use of cross-correlation functions. The sorting and classifying of images was a very serious problem, and once we were able to find a solution with a computer, the whole method was already ready to go. And then finding projection angles is a very serious problem, but we found a solution on how to get started, at least. So here, this is a proof of concept of getting something by first of all how to do alignment of molecules, putting them in superposition, and then forming an average and showing that the average shows more information than the very noisy individual images. That got me started in the whole grant chase. It got with this publication in Science, it got me started with NIH grants, which I have been getting essentially continuously since 1981. So I'm making a big jump now. It's a jump of 10 years or so. So much effort went into it until we got the first three-dimensional reconstruction of a biological molecule, which happens to be a large subunit, a large ribosomal subunit. And this is a depiction of this. Still no ice. no, we used simply negative staining at that time, because this was the only technique of sample preparation that was available. But then soon came the ingenious methods that were introduced by Jacques Dubochet, and then the two technologies essentially came together. The single particle approach of reconstruction and the sample preparation in vitreous ice. So I just wanted to essentially go to the place where ice came in. What stations have I gone through? So I got my diploma in Freiburg, then went to University of Munich, got my diploma and master's, and then I got my PhD with my mentor Walter Hoppe. I got a Harkness Fellowship that enabled me to go to the United States for the first time and visit 3 labs, JPL, Caltech, USC Berkeley, and Cornell. By the way, JPL, Jet Propulsion Laboratory, Caltech, was at the time the best place for image processing. They had the best equipment for this, and I was very fortuitous for me to get into this environment, even though nobody else around me did electron microscopy. I've benefited from their experience and also their hardware in image processing. And the idea of the spider system that I told you about really came from the JPL. They had a program system that was also modular, and it gave me an idea to develop it in this way. And then I spent a few years at the Cavendish Lab in Cambridge as a group leader, and then I got my first permanent position at the Wadsworth Center in Albany, 1975, and joined a little later SUNY Albany as a professor. So I'm going to go through this series. This is the Freiburg study of physics, where I knew nothing about biology whatsoever. Munich, electron microscopy, image processing. Here is my mentor, Walter Hoppe, with one of these very imposing microscopes. It was a Siemens microscope. At the time, Siemens was still in the business, and it very soon, a few years later, dropped completely out of this. And then this wonderful time that I spent with the Harkness Fellowship, and this shows the 3 places where I was at JPL first, and then UC Berkeley and Cornell. Now, UC Berkeley brought me together with Bob Glaser. Bob Glaser has been one of the pioneers in electron microscopy. He characterized the radiation damage of molecules. He also was the first one to experiment with frozen hydrated special sample preparation, but he didn't quite do it in the right way. So it was still some years went by until Dubochet really became effective. And so these 3 places really got me networked with a lot of people, because I encountered students that later became group leaders. I had very intensive discussions and conversations with my mentors, and so this really this experience I drew on much later. And then I was at a Cavendish lab, 73 to 75. So the Cavendish lab the Cavendish laboratory was still at Free School Lane. Nowadays it is outside somewhere, but this is the traditional place where it was first. Here's the plaque. And obviously it's a place that has a very distinguished history in nuclear physics, in atomic physics, molecular physics. And Ernest Rutherford was one of the first directors of the Cavendish. And here there's a whole photo gallery of things that are related to the early discoveries. And here's his discovery of the nucleus. And then, looking back out in the courtyard, at the time that I was there was a barrack. What was this barrack? That was the start of the Laboratory of Molecular Medicine, Laboratory of Molecular Biology, where Max Perutz did his first experiments. So the LMB, which is now part of the MRC, used to be part of the Cavendish lab. And so this is, they moved out and went into another building at the Edinburgh's hospital later on. And here I already showed you this before. So this is where the first discoveries were made with protein crystallography. And then I got an invitation to apply for a position in Albany, and that was successful. And I was invited to start an image processing group associated with a high voltage microscope. This is all in this newly established Empire State Plaza with these very imposing government buildings. And so the Wadsworth Center itself was underneath this building, way underneath. Essentially no light. Okay, there was little light that came from what I call the inverse skyscraper, some kind of a light tunnel. But the important thing is that all the ideas of cryo-EM, all the ideas of the single particle average was done right there, not at Columbia. It was right there. And I was in peace and quiet for quite some time. I didn't have any teaching obligations for 10 years or so. And that's under these conditions, and with some initially generous support from New York State, I got these things done. So now we join, we go back to the actual stations of the research itself. So this is in 1987, essentially. For me, there was the joining of the two technologies. And so the idea is that we have the molecules, they are in a solution on the grid, and they are pipetted on the grid, and initially very thick water layer, and then they need to be blotted to the right kind of thickness, and then the grid is plunged into liquid ethane, which is on liquid nitrogen temperature. And then when this plunging is fast enough, the water doesn't have a chance to crystallize. So the heat transfer has to be very, very fast. And then a new form of water that had not been discovered before is allowed to form, which is called vitreous ice. This vitreous ice is essentially glass-like water. It is as if as if the water didn't even realize that it's been frozen, because everything stays exactly in place. And in these conditions, the molecule is not being crunched, but stays in the native structure. So this was the really ingenious contribution that really made things completely different now, because the contrast was directly related to the density inside of water, and we discovered that we were able to use the same kind of data processing that was successful for negative stain. It was a little bit more tricky, but we managed. So here again, so this is the way the specimen preparation is done, and then you see this kind of flaky appearance. These are projections, real projections of ribosomes. You can see that there's no way of getting a structure out of this, because everything has this salt and pepper appearance, and this is because of the low dose that we have to apply so that the molecule is not being destroyed. This shows us, it simply shows us that we absolutely must average molecules in order to get the structure out. Okay? In crystallography, which exists both in X-ray and electron microscope, this averaging is done implicitly, because the molecules are in regular order. You do Fourier transforms or look at the diffraction patterns, then you essentially get automatic the averages. Here you have to actually make the averages explicitly. So you have to superimpose the molecules that face you in the same direction, and then build up a whole stack of these images that are precisely aligned, and then you get the real structure back. By the way, this is recorded on film, and so the contrast is very inferior. Later on, I will show you images that are arrived by using electronic camera. But essentially, after this convergence of the two techniques, we got the first wonderful images, even though they were at low resolution. But these were the first images that were obtained from these molecules because they had not been able to be crystallized. So there are many, many different hemocyanin molecules that we reconstructed in collaboration with someone who specialized in hemocyanin. And then my pet molecule has always been the ribosome. It developed into such pet molecule because it was beautifully suited for trying out the technique, because it was large. The size is large, which is good for all the correlation-related techniques. It is very stable, which is also good, so we don't have to worry about all the different kind of conformations. And it has high contrast because of the high phosphorus contents. That's how I got into the ribosome. At the very beginning, I didn't know what the ribosome was doing. I didn't know about its importance in the cell. And then gradually it became aware of what it was doing, and I hired biochemists and to set up a wet lab. And so essentially we became a laboratory which was quite interdisciplinary, because it had to represent all the methods development as well as the specialties of the biochemistry. So E. coli ribosome, here's an example of hemocyanin, calcium release channel, all at very bad resolutions like 25 angstroms, 30 angstroms, and so forth. But nevertheless, that was fantastic experience at the time. And then they took this very strange picture of me, the iconic picture. It's like medieval, some kind of a medieval person. It's like a monk, okay. But this is the moment, this was really the moment when the industry realized that there is money to be made. There was someone, I can't remember his name, but he was very stubborn and introduced the idea, and he wanted to get the money for development. At the time it was FEI, and then after some reluctance, they gave him the money to develop very specialized high 300 keV microscope, was called the Polara. Now the significance of this is that it was the first time that the technologies merged with electron optics, instrument control, and vacuum technique. Everything was integrated into one computational framework. So everything could be manipulated and controlled computationally. And this was the reason why FEI and later Thermo Fisher had the big start in this whole field, and all the other instruments fell behind. Hitachi far behind. GOL didn't catch up for a very long time. Siemens had already dropped out completely. Zeiss was an over-designed instrument that nobody could operate because it left too many choices to the users. So that left FEI, and this is the first Polara instrument in the United States. Was in my group in Albany. And then I just have a picture here, which essentially I'm very proud of because it's part of the contribution to biology, the real serious biology. It was just after we got the high resolution, or 25 angstrom resolution of the ribosome, that we were able to actually perform reactions in vitro that mimicked the way proteins are made. So the so-called elongation cycle. So we were able to depict all the individual stations of this process. Each circle of this elongates the polypeptide by one amino acid. So it's a very expensive process. And I'm showing this here together with Anders Liljas because he had just, in 1996, he had just shown this whole circular process, and he had discovered by X-ray crystallography that the two molecules which successively enter the ribosome and exit it again exhibit molecular mimicry. They are completely different molecules. One of them is an actual protein, the elongation factor G, and the other one is a mimicry of that protein made up by tRNA and another protein, EFTU. Okay, so he discovered that these mimic each other. And then we found out the mimicry has a reason, because they bind at the same place in the ribosome, they make very similar reaction and so forth. And it's an ingenious way of introducing the tRNA into the ribosome. And then just a few years later, in fact, it was only, this is just a depiction of 200, 1998, we already had this depiction in cryo-EM of exactly this process. So I'm very proud of this, that we got to that stage at this early, at such an early time. And that was a time when there was nothing known at all about the conformational changes and ligand binding by X-ray crystallography. So here's the elongation cycle. And then, so now I come, essentially at that time, I come to Columbia University, and this is not the place, this is not the place where I am, this is the main campus. I'm at another campus. I don't show it here, but this is my view over the Hudson River. So it's 100 blocks. No, not 100 blocks. It's from 116 to 65 blocks or so north from there. And we are close to the little lighthouse by George Washington Bridge here, together with my group. So at this stage, I just wanted to tell you about what I think are the incremental steps of what's now called the resolution revolution. It started much, much earlier than what you sometimes read nowadays in review articles. The first step was really the whole invention of single particle cryo-EM. And then the next step was a very important step of the electron microscopes that are interfaced with the computer. I showed you this before. And then came, logically, automated data collection, because you can realize that if you have everything wired together. We got much faster and more powerful computers, which were able to then collect data on servers and make sort of real-time decisions right away. And also, more powerful computers were needed for the sheer mass of data that are coming in. And then another step was 3D classification, the extraction of multiple structures from a mixture in a sample. Now this is something that is completely different from X-ray crystallography, because we can have multiple structures. They're all mixed together there. And the techniques of 3D classification that were developed then afterwards make it possible to reconstruct all of them separately. Okay, so we don't have to do this high purification anymore, because the purification is being done in silico. Okay, and then the very last step, almost the very last step, was the huge improvement of image recording quality by a switch from film to electronic camera in 2012, the direct electron detection. Now that took care of the last bottleneck. It was essentially a very trivial bottleneck, because you have to realize we have powerful electron microscopes, beautiful, high resolution. We have all the data processing already, but we had a mediocre capture of the image. Okay, and that was overcome by these incredible cameras. And then, so after 2012, the first publication of an ion channel in 2013 made the entire world aware of the fact what can be done now, that this was going to be the dawn of a completely different kind of structural biology. And so from then on, everything changed, essentially. So here's this giant microscope, Titan Krios, from Thermo Fisher, formerly FAI. And meanwhile, there is a similar kind of large box by JOL, also integrated, and essentially a competitor now, and especially in price. Yeah. And you can see, just for the look at it, at the high quality of and high contrast of the data that come out of there, you can see the individual subunits just by looking at it. In essence, we now have the entire sequence of protocols that leads us from the protein purification all the way to the model building of an atomic model. And so this is now implemented in many, many places. I talked about Spider, but Spider is sort of nostalgic now. Nobody uses it anymore. Unfortunately, it gave so much control over people, for people to develop their ideas. It was intuitive. They could immediately see what a particular operation was doing. Instead, we now have black boxes. Only the developer groups know what's in there and what's being done. So it's a very unfortunate situation. The users, they learn from other users on how to set certain switches and so forth. But this is no longer a real control over the technology. So here is just one product in my own lab, but meanwhile, obviously, everybody was doing cryo-EM and managed to get to very high resolution, to 2 angstroms and even beyond that. But this was in 2016. We had the first wonderful structure of a ribosome. You see different colors. These are false colors that just indicate the resolution. Where you see blue turning into violet, you have the highest resolution. And outside, these other colors mean that you have lower resolution because these appendixes are more flexible. So nowadays, if you type in Google cryo-EM structures, you get pages and pages of these here. It indicate how much this technology has now spread out and where it is applied in. So I'm essentially want to close with showing 4 examples of cryo-EM advancing molecular medicine. There's in one case, it is relevant in fighting cancer. In the other case, cystic fibrosis. And then a whole number of heart diseases. And of course, COVID, which really was a pandemic that brought the whole molecular medicine into general discussion. So here is an example of human CDK activating kinase, and it's a protein complex formed by these compounds and acts as a master regulator of cell growth and division, and regulates transcription initiation in the cell cycle by phosphorylating RNA polymerase II and cyclin-dependent kinases. And due to the central role in cellular physiology, CAK has been identified as a promising target for cancer therapeutics, as a possible target for antivirals. So, in other words, we can know about what this molecule is doing. We might have had the knowledge for a very long time, but we don't know how to develop drugs in order to inhibit certain functions. And in order to do this, we really absolutely need atomic resolution. We might even need more. We might need knowledge about conformational changes as well. But the very first step is really the knowledge of the structure. So here it is in a resolution range of 1.8 to 2.3 angstroms, and that's definitely in a range where drug design is possible. Cystic fibrosis, this is a dysfunction of the CFTR ion channel. And here, again, by cryo-EM, we can identify the places of missense mutations exactly in the structure. And this is the every of these is implicated in the disease. So we can you can appreciate how much the knowledge of the structure, how much it contributed to the drug development. And soon after I got my Nobel Prize, even after the announcement, I got this very touching letter, and I first of all, I didn't even understand it or why it was applying to me. It took me a while. I want to add to the chorus of congratulations that you have no doubt received since the Nobel was announced. I have a special reason to send you a thank you as well. My 7-year-old grandson, Jackson, was diagnosed with CF as a newborn in 2010. So I showed you a low-resolution structure of the ryanodine receptor. Meanwhile, in 2016, we got the atomic structure in a collaboration with Andy Marks and Wayne Hendrickson. And by the way, it took, this was first approached by X-ray crystallography, and they got stuck at 7 angstrom resolution and never got beyond this. And so they tried for 9 years. And then at that stage, we tried cryo-EM, and within a year, we were at near atomic resolution at 3 angstroms. And here is a depiction of various mutations that are implicated in malignant hyperthermia and various myopathies that were all studied by Andy Marks. You see all the different mutations all over the place. And here's another table of mutations that all produce heart diseases. Here's a list of five different syndromes that are associated with these diseases. And again, the knowledge of the structure, and the knowledge, in this case, also of the dynamics is absolutely important in order to address these diseases.
And then it brings me to COVID. You might or might not have heard about the story that just 2 weeks after receiving the genome sequence of the virus from Chinese researchers, the team of McLennan had designed, produced samples of the stabilized spike protein. And that spike protein is important to know the structure of because it's the one that makes the first entry into the cell. And it took 12 more days to reconstruct a 3D atomic structure, atomic map of the spike protein and submit a manuscript to Science. So it was published March 13, 2020. This is a really fantastic achievement, and it was made possible by that stage of development of cryo-EM. So they've obviously at the time there was a proliferation of papers that all looked at the spike protein and its mutations and the way it could be neutralized by antibodies. Okay. So to really wrap up, it's clear that cryo-EM has pretty much taken over structural biology, and many X-ray groups have jumped over to the other technology. Venki Ramakrishnan, who is known for the X-ray structure of the ribosome, is doing cryo-EM exclusively nowadays. And you can see from the number of entries released annually that cryo-EM is really on an exponential path, and X-ray is stagnant now. In conclusion, in recent decades, medicine has become very powerful by leveraging the knowledge of molecular structure. We speak of molecular medicine. X-ray crystallography has been a traditional technique to determine structure of biomolecules, but many molecules do not form crystals, so the cure to many diseases was out of reach. Cryo-EM, which does not require crystals, is a new transformative technology for imaging biomolecules and determine their structures in their native states. Many biomolecules, such as ion channels and receptors, that are hard to crystallize for X-ray crystallographic studies can now be imaged at high resolution. And based on the knowledge of the structure of biomolecules, drugs can now be developed to combat many diseases for which there was no cure. This is the year, this is the summer afterwards with my group on the building where our laboratory was in. Please go to my website, my scientific website, and I put a little oval around this logo Nobel 360, because if you click there, then you can have a 360-degree view of the lab and the surroundings and the specimen preparation area and education facilities. And then some people might know that I'm also prolific in other areas, and in arts and fiction writing. So you're welcome to look at this as well. Thank you very much for your attention.
Thank you, Professor Joachim Frank, for such an informative and inspiring speech. We will be entering the panel discussion shortly. Please have a seat as our staff proceed with the venue setup. 谢谢 Joachim Frank 教授精彩的演讲，请教授先回座。接下来将进行 Q&A 交流，请稍等几分钟，我们先请工作人员布置现场。
Where should I be?
Now, I'd like to invite our panelists to the stage. Please join me in welcoming the 2017 Nobel Laureate in Chemistry, Professor Joachim Frank, Dr. Tsai Ming-Dao, and Dr. Wang Huijun from the Academia Sinica. And last but not least, our moderator, distinguished Professor Zhan Naili from the College of Medicine. They will now take the stage for the Q&A session.
Hello? Is it working? Okay. Okay, so before I start, I'd like to thank Professor Frank once again for delivering such an outstanding and inspiring talk. So now we will start the Q&A session. First, I'd like to invite our distinguished panelist, Professor Andy Wang, Wang Huijun 院士, who is a pioneer in structural biology and also the discoverer of zDNA, and Professor Tsai Ming-Dao 院士, who is the leading researcher in structural enzymology, and also Professor Tsai established the cryo-EM infrastructure in Taiwan to give us their comments or questions. So, Professor Wang, may I invite you to start?
Sure. Well, Professor Frank, I think you have given a wonderful talk in terms of the history of cryo-EM and so on. You briefly mentioned that it may be important in drug discovery, but it turns out that you described that the cryo-EM technique now can resolve the atomic structure of many complex protein and complexes. However, for drug discovery, you need to, let's say, screen different kind of compounds for their binding sites and so on. So it's a very laborious process. So do you think cryo-EM in the end can, let's say, compete? I'm a crystallographer, so I'm asking this question. Can it compete with the crystallography in terms of drug discovery process? Your comments?
I'm really not sure because I'm really not in this business, and I know that there are high throughput developments in cryo-EM as well, and they might be able to give the same kind of throughput that is necessary. I know that the pharma industry is sort of hedging their bets. Some of them have been doing real investments in instrumentation. Others rely on some academic collaborations. But you're probably much better informed about this.
Well, I think cryo-EM can resolve much more complex structures, and many diseases may be associated with this kind of structure. So in the end, I think those structures may not be amenable for X-ray crystallography. So the only way would be by cryo-EM. Thank you.
Yeah, that's a very good insights. And Professor Tsai, may I invite you to share your comments or questions?
Sorry, this is too loud. Well, my first question is, where is the limit? cryo-EM being able to resolve multiple structures or conformations. This could go very far, particularly with computational power improvement. Particularly Taiwan has a lot of IT industry. So do you think we will be able to see like 10% of the protein structures? Or 5%, which
one cannot really push it like this, because you only have a limited data collection.
Yeah.
And then it's all scales up with computer power. So in terms of what can be managed, is probably a million, a couple of million projections, single particles, but you cannot go beyond it. And since you need a minimum number of particles in order to do a statistically significant reconstruction, you can only say have maybe between 5 and 10 different structures in the same data collection.
Yeah. That is already very good compared to X-ray crystallography.
Sure.
I may ask another question. You mentioned the cryo-EM here, but there's a new, or not so new, but a technology called tomography. So what do you think of the future of this electron tomography, because it can view a much larger specimen like cells or organelles and so on?
Yeah, obviously, I should have mentioned it, obviously, because electron tomography has become very powerful, especially together with FIB milling and focused ion beam milling, that's FIB milling. And it's been shown to really yield results that are close to atomic resolution. However, they can only be obtained by averaging. So a typical application is to ribosomes, because you find ribosomes everywhere. Okay,
that's your favorite.
And yeah, sure. So since you have the ribosomes everywhere, you always find a subset that is at the same stage in their functional cycle.
Okay.
And so it's sort of I would say, a cheap way of getting to the higher resolution. There's been a lot of people either doing template matching. So if you already know what you're looking for, and you can find them, you can find specifically where they are realized in the cell. I think this is very powerful. But it really doesn't address the actual question of can I see what they're doing right now, right then? Yeah.
In situ.
Yeah, in situ.
Okay. Thank you.
Yeah, I believe the cryo-EM is a very bright future, and it's currently dominating the field. But then, as a crystallographer, I hope that X-ray crystallography will also flourish by complementing or integrate with the cryo-EM studies. Okay, so now we will take questions from the audience. So maybe Professor Tsang will say something.
Yes, I am Chen from NTU Chemistry. So as our president, Professor Chen, just briefly mentioned, that the cryo-EM is not only limited to biological systems, it can be effectively applied to synthetic chemistry, polymer chemistry, and material science. So from your perspective, so what do you think the key steps needed to further generalize this technology and make it more accessible across disciplines? Because, for example, in Taiwan, there's often a long queue for instrument time. So how do you think the institutions can best invest in infrastructure and training to support this growing demand? Yeah, thank you.
I'm really I don't know very much about material science, so I from what I gather, there are many applications, but I just I don't know why we need cryo in many cases. Maybe the same techniques of data analysis can be done at room temperature. But I don't know the instances in which we have this phenomenon that we have identical structures in many copies. So I just don't know where the application is. Yeah? And also people very often talk about cryo-EM, but they leave out single particle. Okay, many people refer to single particle cryo-EM by saying cryo-EM, but cryo-EM is a much larger field. And I'm the specialist in single particle cryo-EM, but cryo-EM, you might need conditions under which you have to lower the temperature. And then you do whatever you want with the microscopy. So you could have, lattices that you might want to look at low temperature. Yeah, but then all the methods that I've described are not applicable.
And Professor Tsai, do you have something to add?
I think the one direction of growth would be in the mechanism of catalysis, or enzyme catalysis particularly. But I think related to that, time resolution or time dependent, I think Professor Frank has addressed that, but I think he talked about so many subjects, that's only one of the subjects. But that's actually, I think you probably should agree that a major future direction. And the reason is we have been able to solve so many structures, particularly now there are programs to predict structures. But all the structures we have solved in the data bank are mostly static structures or ground state structures. But the functions of proteins and enzymes occur at transition state, or the process of going to transition state. So, and that is chemistry also. So we need to go stepwise to catch the intermediate, even for drug discovery. That is a better target. I mean, since 1970s, it was established that transition state is the best target for drug discovery. Okay. Now, to go to the time-dependent studies, that means instead of doing one structure, we need to do one reaction. One reaction, we need to take 10 structures or 20 time points. Okay. By the way, this is the strength of crystallography still, because the X-ray, the laser X-ray X-FAIR still could do time-resolved crystallography much faster at like nanosecond or femtosecond time scale. Cryo-EM, the entire cryo-EM application is moving into time dependence also, but I think the limitation right now is in the millisecond time scale. But the important point is, to do that we need multiple instruments. We need to increase our instrument capacity, because instead of just doing one structure, right now you have to wait for 1 month to get into the high-end instrument in academia Sinica. Okay? We bought that instrument 10 years ago. It's already fully occupied. Okay? Now, instead of doing one structure, you need to do 10 time points. Then I have to wait for 10 months. One month I do 1 point. Second month I do second point. And that's impossible to do research. So I think the entire Taiwan community, no matter you are doing chemistry, physiology, medicine, or biology, I think we need to recognize this fact that cryo-EM is an essential tool. Okay, it's not a choice. If you don't have it, you're just behind with your ranking or with your research productivity. Okay, that, you know, I think there is evidence, clear evidence for that. So that's what I could offer. Thank you.
Yeah.
So just thanks for bringing up time resolution. Because of the generality of the whole lecture, I did not slip this in. But this indeed, after in the past 15 years or so, that's my main emphasis on time resolution, and the equipment that is needed is really pretty moderate. I would, to put a price tag on it, I would probably say at most $200,000 or so, but maybe even less. But in my opinion, it should really be an instrument that is in every group. Because it so much expands of what you can do with the existing, much more expensive instrumentation. And as you said, we are in the millisecond range, but we can do amazing things in this range, between something like 10 milliseconds and 1 second. There are many intermediate states that we see when we follow translation, and we have already multiple results from bacterial, both bacterial and eukaryotic translation.
Yeah, thank you for the discussion. I'm very happy that our president is in the audience. And also our president mentioned that the stuff matters. Many projects related to stuff matters can be visualized by cryo-EM. So, and Professor Frank mentioned about the importance of having a good infrastructure. So, and okay, yes.
I have a short comment. Professor Frank's lecture clearly showed that the EM in general, including cryo-EM, of course, is very powerful. And Taiwan does not have too many cryo-EM machines. Right. And 10 years ago, I worked with Min Dao in Academia Sinica to push for this. It was a lot of effort. But I think perhaps we have his endorsement that Taiwan should invest many more cryo-EM machines.
Yeah.
Is JOEL machine cheaper?
Yeah,
you mentioned cheaper, right?
They're cheaper, but you have to take this with a grain of salt because the user community is smaller.
I know.
And so nowadays you rely on the network of people who have been using an instrument, so it is.
Many of the Japanese, sorry to interrupt, but many of the Japanese is not so user friendly, and so that's part of a problem.
Yeah.
In the old days, the NMR machine is the same. We have a Brooker, we have also Joe, and after the competition, the Joe just disappeared.
Yeah.
But fortunately, in Taiwan, we have very powerful and extensive synchrotron facility, and the synchrotron really government invest a lot of money, and we establish many beam lamps for different purposes, and so I think cryo-EM should have a similar national facility like this.
Right. Well, this might be the ultimate uses of the synchrotrons, because you can put these large electron microscopes.
Thank you.
Yeah. So maybe we'll go back and forth between students and faculty members. So any students want to raise questions? Yes, please.
Okay, thank you for your wonderful talk. And my question is, you are original in physics field, and later you joined a biology-related topic, and finally you got a chemistry Nobel Prize. Have you ever think about this when you were a student? Have you ever think about this happening when you were a student?
You cross disciplines, from physics to biology, and got a prize in chemistry. So
Yeah, well, I would.
She's wondering.
I would never.
What do you think?
I would never have thought of this. In fact, as I explained to the students this morning, I got into life sciences also in a very indirect way, because as being educated as a physicist doesn't really get you in touch with all the, at least at the time in Germany, and I was the happy recipient of an award that brought me together with other students, including life science students, and that's how I got in touch with them and became aware of the developing fields of molecular biology, molecular genetics at the time.
Yeah.
Yep. I think that's okay. Yeah, Professor Yu.
Wonderful talk, Dr. Frank. Yeah, I'm interested to know right now the limitation for the time resolve cryo-EM. As far as I understand, right now people working on called Kish and Run organelle cryo-EM is of about 4 milliseconds. And I want to know what exactly Fourier transfer equation to resolve this time course in a 3D structure.
I could not understand it. I'm sorry.
My question is regarding the mathematical equation, how to really accurately resolve the time course in terms of interpret this time very short period crystal and try to get a concrete result or in vivo crystal in situ, right? Thank you.
I'm sorry. Wait,
I believe in terms of mathematical formula, there is no particular limitation.
Yeah.
As long as you can collect the image, they will be fine. Okay.
Did you catch it? Or?
The answer is for you.
Oh, I see. All right, thank you very much.
Okay. So, I will take another question from a student. Yes, please.
Thank you for your speech, and I am a chemistry department student. I just want to know. Oh my God, I'm so nervous.
Slowly.
Would you like to say would you like to say something to potentially future chemists or future scientists here? Would you like to share anything?
She wants to know how to get the Nobel Prize in chemistry.
Well, well, obviously there's no recipe for this, and as you can appreciate, there are so many nominations every year, and it is almost a matter of chance in the end, and there cannot be that many Nobel Prizes for the true achievements that are made constantly. And so it's really, as every human enterprise, it has its faults and limitations. And so I consider myself very lucky to have gotten it. And I would have the advice not to strive for it. It is really, it would be a tragedy. It would be a tragedy if you set your life on it and set all your goals on it, and then in the end you don't get it. And so
you don't get the fun of it.
Yeah.
But one very important factor, you must live longer.
That's true. That's absolutely true. So that would be the investment. You eating well, and so on. It's part of it.
Okay, so I'm sorry. There are too many questions, and the organizer told me to keep strict time. So we'll have one last question, please. Yes.
Yeah.
Okay, thank you for your excellent talk to us. So my question is, nowadays we know AI become important technology for all over the world. Do you have any idea in combination of the AI with your cryo-EM in the near future? Thank you.
Yeah, thanks for the question. The AI is a very complicated question because there are particular applications of AI where there's no doubt that it can help us tremendously sorting and sifting through data. And in cryo-EM itself, you know about the very pedantic problem of particle picking. Particle picking is a subjective thing that people have been doing, and then they sort of trained a computer to do it, but it was really very marginal the way it was done. And only through AI, the particle picking became more objective. And that is a major contribution, even though it looks so trivial. The other one is really, about AlphaFold. That has more to do with the interpretation of structures. I noticed from what my postdocs were doing, they use it mainly in order to if you have a molecule, you have the map of a molecule, and then at the periphery, the resolution gets a little bit more shaky, and so now you want to interpret. You want to interpret what is going on there, and you make multiple. There are multiple possibilities, and then you have to change the structure. You have to exchange structures there and so forth. And so if you do this manually, it might take weeks, it might take months. This kind of thing can be done by using AlphaFold very, very effectively. One can't go through. But people generally have incredible expectation of what AlphaFold is doing, can be doing. And to those I say, AlphaFold is just as dumb and as bright as the experimental science that it has data mined, okay? There's nothing outside of it. So the expectation that it can be somehow replace experimental science is really stupid. Okay, and then, but the AI, generative AI, I'm absolutely alarmed. I'm alarmed, and I think this is one of the menaces of our civilization. This is one of the very big issues now, along with climate change, nuclear arms race, biodiversity, and AI. Generative AI. It's a menace, and we have to do something about it.
Yeah, thanks for the insightful comments.
Yeah.
And, well, due to the limit of time, I have to close this session now. It has been a very stimulating, inspiring discussion. And thank you very much for your participation. And please join me to thank Professor Frank, Professor Huang, and Professor Tsai again. Thank you.
Thank you.
Wonderful. Thank you very much.
Thank you all for the wonderful discussion. Please take a seat. Professor Joachim Frank, please remain on stage. we would like to invite Professor Wen-Chang, President of National Taiwan University, to present the trophy to our esteemed speaker, Professor Joachim Frank. Thank you. Please take a seat.现在我们将拍摄大合照。We will now proceed to the group photo session. 请各位贵宾往前方及中间移动，以利所有观众入镜。谢谢。Ladies and gentlemen, to ensure everyone is included in the photo, please move closer to the front and middle of the lecture hall. Thank you. 请各位贵宾往前方及中间集中入座，谢谢。好，我们要开始拍照喽。摄影师在舞台前方，请各位先看向背板前面的相机。On the count of 3, 1, 2, 3。好，那我们再一张。On the count of 3, 1, 2, 3。好，谢谢各位贵宾。各位贵宾，今日活动到此结束，诚挚感谢各位的莅临。为了展现诺贝尔奖得主演讲系列成果，场外正在进行对话诺贝尔特展，欢迎参观，并期待与您再次对话，再次相会。This concludes today's event. We sincerely thank you all for joining us. To showcase the achievements of the Nobel Laureate Lecture Series, we are currently hosting the In Dialogue with the Nobel Spirit special exhibition outside the venue. We warmly invite you to visit the exhibition, and we look forward to seeing you again.